We're going to switch gears today a little bit from air topics to water. And we are very fortunate today to have Sam Cook with us, and he's going to present on some water reuse topics and how they relate to sustainability. Sam is one of our national experts for liquids management, and we're glad that he was able to make some time today to talk to us. So again, thanks for joining. And Sam, I know you've got a lot to cover, so take it away.
All right. Well, thanks a lot, Josh and Laura. Greetings, everybody, and thanks for tuning in to this. It's actually a joint session of Sustain U and Liquids U for water reuse and treatment. And for the sustainability folks, when people usually think about sustainability, the first things that come to mind, at least, for me at least, was energy efficiency, limiting greenhouse gases, of course, sustainable materials management. But I'm here to tell you that water stewardship and water reuse, definitely sustainability issues too. So while you review these session agenda items on the left side of the slide there, I want to just remind you why water stewardship is so important. And so looking at that picture on the upper right, about 6,000 years ago, the Sahara Desert in Africa was actually much greener. It was grassy, even forested. And research has shown that severe changes in shifting weather patterns caused that severe change to occur. And closer to home, you know that large parts of the American West have experienced years of drought. And this past year, it was a welcomed exception, but water is just so important for sustainability. So I'm going to introduce water reuse and how that compares with typical wastewater treatment. And we'll get into some of the details regarding what's happening on the public water supplies and industrial water reuse. Sort of a reuse topic, certainly a treatment topic, and that is the per and polyfluoroalkyl substances, or PFAS, emerging contaminant that's pretty important with the changing regulations. And so water reuse is generally divided into two main categories. There's public, and then there's industrial. And public water reuse covers non-potable and potable uses. Now, what's this term potable? If you're not familiar with it, it just means drinking water. So industrial reuse is divided more into different specific uses. And we'll go through some of those because there's a couple of SCS project case studies. And I can tell you more about that as we go along. So what is the big deal? Water's water. It flows out of the tap. You turn on the faucet. So why all the fuss? Earth's surface is 70% water, albeit it's salt water, and you wouldn't want to drink it. But maybe a little known fact or facts that of all the world's water, only 3% is fresh water, as opposed to salt water. And 2.5% of all the world's water is locked up in either ice or is below ground. Only 1.2% of all fresh water is surface water, and which is easier to get to. So that's the real issue that makes water so important. So water can actually be used and reused. Let's get into some more of the details. So starting with the most basic information about the water cycle, and if you've never seen this before, then it's pretty incredible. But how humans access and use water. So it rains, of course, and water infiltrates in the ground by gravity, and some of that groundwater flows out of the ground into streams. The important thing to see on this graphic is that when you pump water out of the ground, the water table level drops. And if you keep pumping, like at millions of gallons per day, which is pretty typical of municipal water supply wells, and if there's not enough recharge, then the water table just keeps dropping. And it can drop so far that surface water dries up. And this happened, this is historical, but in Waukesha, Wisconsin. It used to be called Spring City. It had so many artesian springs, water was flowing out of the ground, and it was known as Spring City. It's 100 years ago, but that was a fact. And so not only do the springs dry up, but Waukesha's now has water supply problems, and has for several years. And I actually did a project, a water reuse project for a company, industrial soup and sauce manufacturer in Waukesha, and we'll get into that. But all these stories I just pointed out are about water reuse, water sustainability, water stewardship, and just pointing out why it's important. Now there's bad news or challenges, and there's also good news. So among the challenges have to do with cost. Aquifer water, relatively low cost. Cost of surface water treatment is higher. Now, why would low cost be, why would that be a problem? Well, aquifer water often just needs to be pumped out of the ground. That's why it's lower cost, while surface water requires treatment. And it's equipment, chemicals, labor. Another challenge is the number of chemical pollutants that can occur in our drinking water. And that list of pollutants just keeps on increasing. And like I said, we'll be talking about PFAS, but there's also endocrine disruptors like bisphenol A. 1,4-dioxane is another emerging contaminant. The list goes on. And there's other challenges listed here that are obviously, they can severely affect the water supply. But the last one, I just want to spend a little bit of time on that. It's rooted in, and this may sound crude, but there's a negative slogan that contributes to the public stigma. It's called, or the statement is, toilet to tap. And it's sometimes brought up regarding potable water reuse. For those who are a bit shocked by that statement, and I kind of am even just saying it, we'll talk about why this is so untrue, and really it's just an uninformed way of thinking. And we'll get into some of the details. But like I said, there's good news. And we started, the Earth's surface is covered by 70% water, mostly salt water, not fresh water. Very small percentage of the Earth's water is fresh water, but fairly simple and overall inexpensive ways of desalination have been developed. So that's really good news. But they do require a change of infrastructure. So that's why you don't see a lot of that going on. But you will, I think, in the future. And with nature having built-in treatment, that's a major advantage. Humans have benefited, as is often the case, from nature and how water infiltrates in the ground, gets filtered through the Earth's built-in treatment system of the soil and the rock below the surface. Up on the surface, where water needs to be treated for potable water use, we do know how to treat it, and we've been doing it for a long time. So that's good news too. And make it so the water that gets treated has a chance of getting reused. There are federal guidance, and they provide the leadership. It started going in the 1980s, and it also provided some funding. So then certain states like California, Arizona, Maryland, New Mexico, Florida, and many others have developed regulations and guidelines. So I want to emphasize that there's no standard federal regulations on water reuse. There's only certain states. But industry has also stepped up, and like I'll show you with an SCS project example that I was involved with, and then one that Steve Stewart and Coquille Bansal worked on. So let's dive into that a little bit. So first, Steve and Coquille's project. Here's a graphic from that steel mill project that they worked on, and this. So greater than, right in the middle there, greater than 4 million gallons per day are withdrawn from the river. Steve and Coquille found over 2 million gallons per day of potential water losses. And there's a lot of other details. But because of those potential water losses, Steve introduced this steel client to David Hostetter and Sam Rice with our remote monitoring and control group. And they're proposed on setting up water meters for submetering at various steel mill processes, and that those processes use large amounts of water for cooling and other industrial uses. So that proves out that classic sustainability statement that you can't measure or you can't manage what you don't measure. So I'll say it again. You can't manage what you don't measure. So Steve and Coquille that can give their own presentation on this project did a really good job on this. I was very impressed. So I won't go into further details, but in conclusion, this client wants to improve their knowledge of their water usage through this report. And now they could save hundreds of thousands, even millions of gallons per day, potentially. And I'll point out that the savings are not only the raw water savings and treatment of that raw water savings, but also wastewater treatment savings, electric energy savings, natural gas savings, chemical savings. You can see that industrial water reuse and water stewardship is much more than just water. And previous slide was on the industrial side of water reuse, which is SCS's current primary area of focus. The other side of water reuse is public water reuse, or what I sometimes call municipal. And it follows its own cycle that's shown here. Start at the bottom of the receiving waters in that green box, which can be groundwater or surface water. And that becomes the blue water supply on the left. And after use becomes the purple wastewater right in the middle. Now, here's where some of the water reuse comes in. If the wastewater is treated further, and we'll get into that treatment further and what that involves, beyond what is normal primary, secondary, and tertiary treatment steps, and we'll get into that a little bit too, then the lower left yellow reclaimed water can be added back to the water supply. And meanwhile, swimming around all this is the orange stormwater that also has its place in water use reuse cycle, as you can definitely see. So what does public water reuse actually look like? So here's an example of public water supply that includes reuse. It's in Orange County, California, where the first SCS office is located near to that in Long Beach. What you see in the photo is part of the world's largest treatment system for indirect potable reuse. And water goes through microfiltration membranes, reverse osmosis membranes, as well as something called advanced oxidation processes that involve ultraviolet light and hydrogen peroxide. And all that creates a very, very pure water that ends up in the Orange County groundwater replenishment system. And these white cylinders that you see in the photograph there, the water district's reverse osmosis membranes are inside there, and the RO permeate or clean water exits out the end of the RO units through those gray curved tubes. So you can see it's a pretty big system, and this is just part of it. So staying on Orange County, microfiltration, the reverse osmosis, those membranes talked about, and the advanced oxidation processes, those create that ultra pure water that's injected into the ground. And this graphic shows how that works and how of the 130 million gallons per day, that 30 million gallons per day is injected to keep the salty seawater from the Pacific Ocean from intruding and getting into the freshwater aquifer that's more inland. And 100 million gallons per day is infiltrated through the ground and becomes part of the drinking water source that's pumped from the drinking water wells. So for Orange County, they started this process. Their first initial system was built in 2008, was upgraded in 2015, and then the latest upgrade was completed this year in 2023. So going from more local California to more national, how widespread are water reuse regulations and guidelines? So this graphic shows that as of March of this year, 30 states have regulations or guidelines regarding landscaping water reuse. So taking treated wastewater and using for lawn, garden, even farm irrigation. And the blue states have the regs and the guidance, and the gray states do not have the regs or the guidance for landscape water reuse, or at least not yet. So this graphic shows 15 states that have regulations and guidelines regarding potable drinking water reuse. So as you look at this map showing the blue states that allow potable water reuse, you can compare that with the landscaping water reuse states. And I'll just go back to that slide. So this is landscaping water reuse. I'll go forward, and there's the potable water reuse regs and guidelines states. Here's the third and final graphic, and there's a bunch of these if you're interested in this. You can see the website down at the bottom. So this shows the 15 states that have regulations or guidelines regarding industrial water reuse. So of the many types of water reuse, the most stringent water reuse treatment is for potable drinking water reuse. So starting at the top of this graphic, there's the primary, then it moves to the secondary, and then tertiary treatments. Then that's followed by disinfection. So a lot of you liquids management folks might recognize that that is typical activated, that's typical, basically the way that wastewater is treated. So the activated sludge treatment process. Normally, the treated wastewater from those first 3 or 4 steps, and sometimes tertiary treatment is not incorporated in the activated sludge treatment process, but primary treatment, secondary treatment, disinfection always are. But so normally treated wastewater from those either 3 or 4 steps is discharged directly to surface water. And so for potable water reuse, it requires the remaining steps, starting at the middle left, the microfiltration. Then there's reverse osmosis. There's that ultraviolet light advanced oxidation process. And then in this case, there's also a degas step with remineralization of the water using lime. Once you've run through reverse osmosis, it pulls all of the minerals out. And so the taste of water can be a little astringent if you don't have it remineralized. So use lime for that process. And then degassing to remove oxygen for corrosion resistance and things like that. So for potable water reuse, there's multiple robust treatment processes added to that normal wastewater treatment that we talked about with those initial steps. So you can see how that phrase toilet to tap is such an untrue statement. And so now let's get into some more of the industrial water reuse details. And so I did a project that has water supply issues. And in this case, the reason that they were looking at in the 2 or 3 years down the pike, they were looking at as much as 3 times the cost of what they were paying currently for water that was going to be supplied 2 or 3 years from then. Really cool company. On this graphic, you can see how the industrial water was being used. And just so you know, industrial water reuse projects, the first step is always establishing the water usage through process submetering. We were able to use some of their submetering that they had already. So you can see that in this graphic, the blue water usage or process cooling water, that's the single highest water usage. And their process cooling water is used by what's called a once through cooling type of system. And like the name suggests, it means that 54-degree potable water is run through the cooling processes, heat exchangers, and water that is just running through one time cools the hot product. And then that water that hasn't been in contact with the product, it's going through a heat exchanger. So it's not in contact, it's cooling it through the heat exchanger walls. That water is then discharged to their storm sewer. So you can see in the box in the upper right, the term credit meters. And credit meter, what that is it measures the process water that's discharged through the storm sewer so that at least you have to pay for the wastewater treatment because it's going to the storm sewer. It's not going to the municipal wastewater treatment plant. And that's based on the credit meter. That they can take the volume of the credit meter, subtract that from the overall city water flow, and then deduct that from what they charge. But we found much more savings than just that small credit meter savings. So our industrial water usage assessment, what we discovered was using what I would term as a high total dissolved solids water for their cooling towers and their boiler makeup water. So why is that an issue? Because cooling towers and boilers, as you know, evaporate water, and that causes the water that is not evaporated to increase in dissolved solids, and that causes increased concentration. Higher concentration total dissolved solids water is then blown down or simply wasted down the drain to get rid of that high dissolved solids water. And if lower dissolved solids water is used as makeup water, then a lot less of that blowdown has to occur. So in addition to, so what we did is we recommended that reverse osmosis be used to reduce the total dissolved solids in the makeup water for the cooling towers and the boilers. And that made it so that when you feed a lower concentration of water for your cooling towers and boilers, you don't have to blow down even close to as much. So in addition to those issues, the volume of once through cooling water wasn't being controlled. And we already talked about once through cooling water. So that cooling water was being used, and more was being used of that once through than needed to be. And it was just simply being wasted down the storm sewer after only passing through the cooling system once. So you can just imagine the issues that would cause as far as cost. So based on those findings, we calculated the amount of not only the water savings, which is shown right in the middle, but also the chemical and natural gas savings that's just to the left of the water savings. And when compared to the estimated cost of the engineered solution, which is shown close to the right, the annual savings resulted in some impressive simple payback values that are shown on the right column. So look at that. It's 3 years and 0.2 years, with about 2.5 months. And I will point out, so these are some good projects, even for industrial concerns, which a lot of times have a 2-year or 3-year simple payback requirement. So I'm just going to point out that the last 2 engineered solutions proposed reusing once through cooling water for either their nightly complete plant sanitation. That's what that sanitation reference is. So that's their cleaning, where they clean the entire facility. The once through cooling water was still clean water. So why not use it for a purpose that's not related to production? And there's also, if they couldn't use it for sanitation cleaning, then a longer payback reuse would be reusing the clean water for cooling tower makeup. You can see that on the bottom. So I included this slide kind of for the liquids management folks, and also just because reverse osmosis is such an important part of water reuse, and that's for both public and industrial projects. And you can see listed on the left, for example, a SCS specialty, deep well injection. And you can see how that compares in cost with the other disposal methods, and the costs are given in dollars per acre foot, and that's a way of measuring large quantities of water. It's basically a foot of water spread out over an acre, which is 43,560 square feet. But costs are also given in more common dollars per 1,000 gallons. So you can see that deep well injection is overall the least expensive, but not all locations can install deep injection wells. So you have these other methods of disposal for concentrate. And this information is a little bit dated, it's 2015, but the comparisons are pretty much consistent with what you'd see in 2023. So in this future of water reuse, I'm giving you some of my predictions, which aren't too difficult to imagine, not really out there that much, but the first one is already happening. And should gain more acceptance as time goes on. So instead of wastewater treatment facilities, the name has been evolving is water reclamation facilities. And so that implies, instead of it being waste, it's more like it's a resource that can be reclaimed. And surprise, surprise, second bullet, the cost of water will probably increase, as well as availability of water, and those sorts of challenges for potable reuse can be expected. So industries will want to save not only the cost of water, but the cost of disposal, chemicals, natural gas, et cetera. And so these are just some predictions, and water reuse is only building. And I think I'll just go ahead and go. So the rest of the presentation is on that per and polyfluoroalkyl substances, PFAS. And just in case you aren't familiar with PFAS, I'll just do one paragraph sort of intro. So PFAS is a large group of man-made chemicals that have been in use since 1940s. Examples would be firefighting foams, consumer products like Scotchgard, on couches, on carpet. And the reason that PFAS have been so popular and been used is because of their superior heat resistance, thus the firefighting foams stain resistance, like your Scotchgard, for the carpets and Gore-Tex, clothing, furniture. They also have superior surfactant properties. So there's, as far as the number of PFAS, it's this huge group. And so there's a list called PubChem. And if you're not familiar with that, that's the largest list of chemicals in the world. They list approximately 6 million PFAS compounds. US EPA lists about 15,000 unique PFAS chemical compounds. Now, PFAS are problematic because they're very persistent in the environment. It's that carbon-fluorine bond. It's the strongest bond in nature. Very persistent and don't readily break down. And further compound the problem is PFAS have been found to be toxic to humans and other life. So it'd be carcinogenic, cause low birth weights, cause increased cholesterol formation, things that you, of course, don't want to have happen. However, if you like chemical names, then you will love PFAS. So here in this graphic, you see that start with PFAS and then the classes of polymers and non-polymers on the near the top, and then you have the subclasses, groups, and subgroups. I'll draw your attention to the middle column and the first gray, the fluorotelmer substances. We'll get into those a little bit when we talk about evaporators, but not only are PFAS persistent in the environment, but there's also a volatile subset called these fluorotelmer substances. And so they can volatilize. Anyway, the PFAS problem, as you can see, is widespread. And this graphic shows projected number of contaminated sites at over 57,000, it's quite a few. So landfills, they would be considered among the purple dots because they're considered more of an industrial facility. And the green dot, you see the major airports would be green dots. Those, when I was looking for those, they're kind of obscured. I mean, they're showing up some places, but mostly obscured by the other facilities. But just realize that all the airports that have firefighting training facilities, those would have significant contamination. So with so many contaminated sites, wanted to show that there's a full array of treatment technologies that can address the PFAS issue. We're going to be concentrating on talking about a few of these. And so in the upper right, those will be the most mature and also the most practical. So you see the x-axis is stage of development. That would be mature and feasibility, moving to the right. So the ones on the far right are the most feasible in their stage of development. And then the y-axis, range of practicality. The ones that are near the top are the most practical. And so you see deep well injection is way to the right and way up top. But you also see activated carbon, our reverse osmosis, nanofiltration, foam fractionation is up there too, ion exchange. And we'll be going into more of those, as you can see on this graphic. So I've chosen a few of those more proven treatment technologies, and we'll get into those. Our old friend, reverse osmosis, again, deep well injection, gain more experience with foam fractionation, as well as several other technologies. And there's a distinction in PFAS treatment or management technologies. And those are ones that basically separate PFAS from the water that's being treated, and then those that actually destroy the PFAS. And so of the ones that destroy, there's thermal, PFAS destruction, and then supercritical water oxidation, the fifth one down. All the rest of those, these are listed on this graphic, are separation technologies. So reverse osmosis. So this is an SCS project site, and reverse osmosis is excellent for PFAS as well as other constituent reduction. And it can get you to non-detect concentrations. And for this landfill leachate treatment site, there's one of the two RO units is shown in the center of the image there. And there's 5 horizontal RO membrane housings. If you recall that picture from Orange County, this is what the whole module looks like. Those white caps that you saw in the Orange County photo. This is showing a photo of the full. And so so the 5 are around the small white poly tank, and like ultrafiltration membranes, the small pores in the RO membrane allow water to flow through the membrane, but then the PFAS and the other constituents you see listed here remain on the concentrate side of the membrane. So permeate, that's the name for what the clean water is. It's treated and it discharges out the end, and I'll show you a close-up of what the RO membranes look like. And then the concentrate is usually for landfills is recirculated back up to the landfill. So here's what the reverse osmosis membrane cartridge looks like, and there's other types of membrane configurations, but this spiral wound membrane does very well for landfill leachates, and the permeate ends up going out the center hole once it passes through the membrane, and then the sort of off-white colored flutes at the end, that's where the concentrate flows out. So deep injection wells, those are used to send wastewater deep into the earth. It's far below drinking water aquifers, and it's separated from injection water by geologic confining layers. When I first heard about deep injection wells, I was wondering, is that really a good idea? And since working with Monty Markley and Stephanie Hill and others in the UIC, the Underground Injection Control Group, it's actually a very viable way of containing PFAS and other contaminated waters. So this photo was taken during the installation of an SCS site, SCS project site. Deep injection well is on the mast on the right, and then there's a monitoring well that's also installed, and that's the mast on the left. And the deep well was installed about 3,500 feet below ground surface. And another treatment method for PFAS is foam fractionation. And let's follow the lines here. So to create foam, you need air. And so the bottom blue arrow is showing the air into the facility. And this is part of, it's called a low energy evaporative fractionation system, or LEAF system. And this is being repped by our friends at the Leachate Management Specialist, Brad Grandley. And so the air comes in the bottom, the air goes out the top. So you see in the upper right, the leachate comes in. And for this example, it's 50,000 gallons per day. And then the leachate goes out after it's run through the treatment at 49,500 gallons per day. So obviously 500 gallons per day ends up going out in the upper left as foam. So I'm going to show you one of the least exciting videos that you will ever see, probably in your life. But just look closely at the little foam cap there on the left side. So that foam is coming right out the top. And then there's another version on the right. And if you didn't have enough of the foam belching out on the left, then I wanted to show you this one. So, and I found that as I try to advance, it goes through all of the videos again until finally I get to the next slide. So, if I didn't know that was going to happen, I would probably think, well, my computer is freaking out right now on this video. But sticking with the foam fractionation, you can see here, and there's a lot of information here, but look at the raw leachate, and let's just follow PFOA, the second one down. So the raw leachate feed was 1,400 parts per trillion, and it's treated to below detection limits at 11.1 parts per trillion. And again, this is parts per trillion, which is 10 to the minus 12. And so then look at the RO reject, which foam fractionation has a particular good application for. And you can see that the feed for PFOA, 12,500 parts per trillion. The foam is much higher in parts per trillion. And so you can see in the graphs to the right, just how much the different PFAS constituents have been reduced. So another leachate PFAS treatment methodology is using an evaporator. Like I said before, that fluorotelmer, in this case, fluorotelmer alcohols, those are the volatile constituents that can actually pass out of the evaporator if they're present in the leachate or whatever other wastewater is being evaporated, and be discharged. There's some other facts there regarding evaporators. They can operate based on landfill gas or waste heat, and operating temperatures and a sludge does remain. So just like the RO has a concentrate, evaporators also have a concentrate. Here's thermal destruction. So those other ones were separation technologies. This is a thermal destruction technology graphic. So this is showing plasma, and this is more of a research cell, but you can see the colorful purple plasma that's extremely high temperatures. So PFAS itself normally requires greater than 1,800 degrees Fahrenheit to break that carbon-fluorine bond. And regenerative thermal oxidizers operate around that temperature. Other incinerators also operate around that temperature. So those are very interesting from a research standpoint regarding thermal destruction and how you can get energy from waste using those. But it does require a lot of energy if it's not self-sustaining. So here's another destruction technology. We talked about supercritical water oxidation, and it operates, you see that red in the graphic there, that red supercritical phase. So that's above 704 degrees F or 374 degrees C. So pretty high temperature, and then also greater than 218 atmospheres, which is essentially 3,200 PSI. So very high pressure, high temperature. This takes a lot of energy, obviously, to get that pressure and temperature. And it's really good for reverse osmosis concentrates and the kind of concentrate that comes from foam fractionation, which is called foamate. And just a little factoid, approximate cost, treatment cost is around $90 per ton. The waste does have to be pumpable, so it doesn't handle solids. So here's supercritical water oxidation. These are the steps. And so you start in the left side with the wet waste. It goes through a heat exchanger, then into the reactor, then the economizer. And the economizer is basically taking that high heat that's coming out of the reactor, and it's utilizing that heat. And then there's a separator as well as a cooler. And those are the basic steps of supercritical water oxidation. Also talking about ion exchange as a leachate PFAS treatment. This is an adsorption form of treatment. And so you see that little graphic is representing a vessel. So you got your influent coming in the top, effluent going out the bottom. You've got a media, a resin type media, and that's that ion exchange media. And so the negatively charged PFAS ions and other contaminants you want to remove using ion exchange are attracted to the positively charged ion exchange resins. Another adsorption method of treatment is with granular activated carbon, and you see an example of carbon on the left there, a little pile of the little granular activated carbon granules. And again, this is another adsorption form of treatment. PFAS adheres to the positively charged sites on the granular activated carbon. It flows into the vessel that you see, and then passes through the granular activated carbon and then passes out. So here's an example, and just wanted to show how effective granular activated carbon is. These are some rapid small-scale column tests. So this is bench scale type of testing. The important thing here is that you see on the x-axis, you see that there's tens of thousands of bed volumes. So what that means is that the water has passed through these bed volumes, hundreds, thousands, tens of thousands of bed volumes, the flow rate through the granular activated carbon. And you see that it continues to remove the PFAS, in this case, perfluorooctane sulfonate, PFOS. So, and when comparing the two adsorption treatment methods, we've got granular activated carbon ion exchange. These are hypotheticals. I just wanted to give some cost information. You see that granular activated carbon for capital costs there in the second row that shows numbers. Capital cost is much higher than the capital cost of ion exchange. Turns out, in this case, for these hypotheticals, ion exchange is about 7% less expensive. So that's my talk on PFAS and on water reuse. I wanted to just give a shout out to my fellow liquids management SCSers. These are folks with Nathan Ham being the national leader for the liquids management group, doing a fantastic job. To see these folks, they would know who to call, who to contact if there were PFAS issues, if there was any sort of leachate or other wastewater issues. If they don't know themselves, which they probably do, then they know who to contact. A closing final thought, 1 part per trillion, this is going back to the PFAS, it's 10 to the minus 12, like I said, and that's equivalent to 30 seconds in 1 million years. That's how small 1 part per trillion is. So I will leave you with that thought. And if there's any questions, appreciate your attention.